So the next thing we're going to be looking at is Stokes Law. Stokes Law is drag for an object that is moving through a fluid. Stokes Law, though, was originally defined in a very unique set of circumstances. Stokes made up a number of assumptions regarding these and only had to work with a very limited parameters. So the first assumption is that the movement or the flow of the fluid is laminar. So what does a laminar flow mean? Laminar, the opposition of that would be turbulent flow. A turbulent flow would be, let's say this is my pipe. Turbulent flow would be it moving around in odd directions inside of the tube. So it's not moving in a nice, uniform, flowing manner. Laminar flow, on the other hand, is the ideal situation, and a lot of physics we deal with the ideal situation. So we are going to have flow that is moving straight through our tube without any hindrance. Now, even if we do have most ideal situation, but even if we do have a more realistic flow, our more realistic laminar flow is going to actually slow down towards the edges and speed up towards the middle. The reason for that is you have a fluid that is interacting with the walls. So that fluid inside is being pulled along at the edges rather than being able to just flow through freely through the tube. When Stokes came up with this, he came up with the idea that it's going to work in laminar flow, so in the ideal fluid situation. He also made the assumption that the object moving through is going to have a smooth surface. Again, lovely idea in physics, mainly because, let's face it, my arm has hair on it. We have clothes that cause drag. They are going to flap, they are going to move. For Stokes' law, let's get rid of all of that fancy stuff and just say it's perfectly nice and smooth and there's nothing that's going to cause additional interactions going on. The next one, it is a homogeneous fluid. What does homogeneous mean? It means that it is going to be the same all the way through. In this situation, we're talking about all of the fluid having the exact same consistency all the way through. Finally, the last assumption was that the particles inside of the fluid do not interact. This isn't always true. Some fluids, let's say water, is actually polar. It has a positive and a negative charge, so therefore they will actually quite happily interact with themselves. They'll actually clump up, and that's why water forms little beads of water on a surface. Because they're polar, they're actually attracted to themselves, and they will actually, instead of just being a lovely flat sheet of water, they will clump up together, which is actually rather cool. So, Stokes came up with the equation for drag. He came up with that our force due to drag is going to be equal to, well, we need to take into all of these parameters, right? So he tested this out. He tested it for the most simple object that he could possibly think of, sphere. Spheres are very simple. We just want to drop them down and they're the same distance all the way around. One of the key defining features of a sphere is that it has a radius. So the larger the sphere is, in a sense, we're expecting it to have more area, more volume, more surface area. So therefore, it has more interactions with the fluid. So it's going to be proportional to our radius. If we move faster through a fluid, are we going to experience more drag or less drag? More. When you go for a run, you can actually feel the wind more against you than as if you are walking. The same way as if you try and run through a water, it actually is a lot harder than walking through water. If you increase your velocity, you are going to experience a higher amount of drag. So our velocity is going to be part of it. The next thing we need to take into consideration is the fluid itself. And for that, we use the dynamic viscosity. And this is actually the eta symbol. The dynamic viscosity is a measure of pressure, so pascals times by seconds. But our dynamic viscosity is a simplified version as well, so we can just work with that at the moment. You're not going to need to memorize all of the different dynamic viscosities of all of the different materials or anything like that. If you need to use something, you would either be asked to solve for it or you would be provided it. Finally, it's a sphere, so we need a pi. But this relationship didn't work. When Stokes went through and actually tried and tested this formula, it did not work. Turns out there's a 6 in the front. And this actually came about by him testing it.